Now before we talk about maybe let's consider this. Now one of the most famous multistage amplifiers and a classical multistage amplifier is the Cascode Amplifier. Now so far we did not worry about the frequency response. This is because of the reason that in most of the applications the signals we are handling are, let us say, assuming we are taking the signal from a typical sensor, the signal frequency would be of the order of at the most, let us say, a kilohertz, most of the time much less than that. So therefore the frequency response is not an issue. So this is why we said in an op-amp, when they designed it for a much lower frequency. So an op-amp is not supposed to be used for frequencies above 1 kilohertz. So next time when you are tempted to use an op-amp, be careful. This is because of the fact that it has a finite slew rate, and that finite slew rate has to do with that compensation capacitor which is put inside, which we talked about. Now there are cases where you need high frequency response. Now you can think of one such situation as a video amplifier. Now in this particular you are seeing me remotely because there is a camera looking at my face, and that the signal of the camera is typically the order of 5 megahertz. So when we talk about a signal, a sensor signal, the highest you would always get from a video signal. A video signal has the highest. Now if you try to make a video amplifier, and if you try to do it, you would find that it is extremely difficult. Now this is because of the reason that the frequency response, anything above a megahertz is very difficult, especially if you try to build it around a discrete amplifier, is extremely difficult. And from our discussion yesterday, we said that the frequency response of a common emitter amplifier is quite small. So coming back to the comparison, we can add one more column. We could add frequency response. Now a common emitter amplifier has, let us say, low to medium. What we mean by low to medium is that typically a common emitter amplifier, the high frequency cutoff would be somewhere of the order of say 1 megahertz or so, and most of the time you do not even get 1 megahertz, typically 100 kilohertz, 200 kilohertz, that kind of order. So that is what we mean by low to medium high frequency response. So let's put the word high frequency response. Now common base amplifier, which we talked about yesterday, is very good from this point of view. Common base amplifier has very high frequency response. Now again, if you build a discrete amplifier, a common base amplifier can give you quite high frequency response, definitely in the megahertz region. Now a common collector amplifier also has high frequency response. Now so we see immediately a case for cascading different stages. If you remember, we said the basic philosophy which we follow in a multistage amplifier is to bring in the advantages of different stages and choose them and order them in such a way that you finally minimize the disadvantages and then you kind of cash on the advantages. So let us think of a scenario which we just now talked about, where we said we talked about the Cascode amplifier, which is nothing but a cascade of a common emitter stage followed by a common base stage. Now this is a typical diagram with biasing and so on. Now what we have here, you have the input coming here at this side. Now the first stage is our familiar common emitter stage. Now what we see here is that the collector, instead of a load here, this is actually feeding to the emitter. Now we know that in a common base amplifier the input is between the emitter and base. Now you can see here that the base terminal is grounded through a capacitor. So for AC the base terminal of the second transistor is at ground potential. At the same time it is biased through these resistors. So you have a proper biasing at the same time. For AC this is a common base. Now what happens is, because we have the advantage of the high frequency response, this cascade would give you the almost the same frequency response of a common base stage. At the same time it would give you the input resistance which is that of the common emitter stage. So this is a very good classical example of taking advantage of the stages and ordering them in such a way that you get the best things. So here the common emitter, common base is poor from its point of view of very low input resistance, whereas a common emitter has, let us say, kind of medium input resistance. So the first stage is a common emitter. So this particular cascode amplifier would give you quite high frequency response and is very commonly used. So if you think about ever a discrete high frequency amplifier, you need to use a cascode stage. Now the output is again taken from the output of the common base stage. Now the voltage gain of this combination would be the same as the voltage gain of a single stage. Now because of the cascade between the common emitter and the common base, if you split this as two separate amplifiers, you would see that the effective voltage gain of the first stage, which is the common emitter stage, is unity. Now we know that we had a disadvantage in terms of the high frequency response in a common emitter amplifier because of the Miller effect, and the Miller effect came into picture because of the emitter, rather the collector and the base terminal of a common emitter having a high negative gain, and we said that amounts to multiplying the capacitor between the C mu capacitor by the voltage gain, and that gave us what was called the Miller effect, and that reduced. In this particular case the voltage gain of the common emitter would be just unity, and therefore the multiplication of that C mu which we talked about does not happen. So this is how a cascode amplifier gives you the same voltage, almost the same voltage gain as a single stage, the same time much higher high frequency response. Now there are also very popular cascode amplifier in IC form. One such form, there is a very popular IC which has inside just 3 transistors. Now this is typically how a CA3028 would look like. Now it has a few resistors also put there, but primarily the way it is connected here, you could use this particular IC in a variety of application. You could use it as a differential amplifier, in which case you could design a particular current for this. You can by putting external resistors, you could design as a particular current here, and you could operate it as a differential amplifier by putting external resistors. Now another very common use of this particular one is its use as a cascode amplifier. Now these ICs here are, rather these transistors here are chosen to have quite high frequency response. So you could design the this particular transistor, the first transistor, which can be designed as a CE amplifier by putting external components outside, and you could design the second transistor as a CB, a common base, again by appropriately biasing here, and you would get a fairly high, I mean you can, let us say, not quite a discrete amplifier, but you have a like a hybrid situation where you could have a mix of IC, the advantage of an IC fabricated transistors, matched transistors, extremely high quality transistors, and our own design. So this is also a very popular, there are quite a few number of these types of ICs which are available for this type of applications. Maybe I could just talk about just one or two cases of, let us say, again cascades. Let me, before I come to that, now let us think about one or two cascades. Now we know that the common emitter amplifier we know has, let us say, low to medium input resistance. Now if you want to jack it up, otherwise common emitter amplifier is a fairly good one. Now if you want to jack up the input resistance, one easy way of doing that is to cascade it with a common collector. So if you have a common collector at its input, then we can get high input resistance. Now in case we want to have, let us say, in an application what we are interested in is to get lower output resistance, then we can think of a CECC. Now so there are many such combinations we can do. Now interestingly, we can also think of other combinations. One such combination is a CSCE. We know that in a common collector, even though a common collector common emitter cascade would give us, let us say, a fairly high input resistance, the input resistance is still not that high. Let us say that you are happy with a common emitter amplifier except for its input resistance, and you are looking at an input resistance of say 1 megohm, in which case you have to either go for a Darlington emitter follower at the input, or there is another solution. You could use a common source amplifier. Now Professor Mahesh Patil has taught you JFET. Now these days JFETs are not commonly used, but you may be having some of these experiments in your colleges. Now JFET is an extremely good device. In fact, JFET is the best device in terms of low noise. It is an extremely low noise device. Now a JFET, as we know, has extremely high input resistance. You could have easily 1 megohm, input resistance of 1 megohm easily. So if you cascade a common source and a common emitter, you could get a cascade. In fact, you can even have, because of the common source amplifier, you can get some slight gain also out of the JFET amplifier. But as you might know, a JFET amplifier, because of the low transconductance, JFET and MOSFET amplifiers cannot give much gain. So that way a BJT can give you much higher gain. Now I thought I will spend maybe another 5 or 10 minutes on what could be kind of a methodology or some suggestions for teaching analog electronics. Now in my teaching experience for the last about 19 years, it has always been a challenge to teach analog electronics. It has always been a challenge. Now in a typical course which we have in all IITs in the first year or the second year, called Introduction to Electronics or Electronic Circuits and Instrumentation, the biggest challenge is to keep the students interested. So I have a few suggestions. Now when we come to analog electronics, now from my experience I always found that students generally find digital electronics much simpler. In fact, when students come for interviews, MTech interviews, if we ask them what question should we ask you, the answer is almost always, sir, ask something digital, don't ask analog. Now analog electronics, teaching analog electronics is always a challenge. Now at the same time there is a big debate today, should we teach transistors, should we teach discrete circuits anymore, because most of the time when you talk about an application you might have already noticed that there are lots of disadvantages when we talk about a discrete amplifier. So why should we teach discrete amplifiers? Now the major reason is discrete circuits, or let us say discrete amplifiers, are the best in terms of teaching concepts. Now today afternoon you have a BJT amplifier, common emitter amplifier. Now I do hope that all of you get the circuit working, but I am sure at least 50% of you would have difficulty. The reason being, analog electronics, unless you design everything properly, unless you connect everything properly, unless everything is correct, things won't work. And finally, if things don't work, how do you interpret? So discrete amplifiers, let us say a simple amplifier like a common emitter amplifier is one of the best to teach concepts. The concept of a signal, the concept of amplification, the concept of non-linearity, the concept of overload, all these things are very easily taught through simple discrete circuits. So we could think of the study of discrete circuits or discrete amplifiers, or in fact multistage amplifiers. In fact multistage amplifiers today you would never ever find discrete circuits being used for multistage amplifiers. You would almost always have a simple IC which would be much cheaper than all the discrete components you put in a multistage amplifier. But the advantage of building a small circuit is that lot of concepts are taught. Now I strongly encourage all of you as my fellow colleagues as teachers to encourage your students to get enthused with experiments. Now unfortunately in our country, if there is one decay, let us say in technical education, this is the area of decay. There is hardly any experimentation in the labs. Now to do an experiment on a common emitter amplifier, you do not need any sophisticated equipment, you only need a power supply, a breadboard or a microboard, a few components and an oscilloscope and a function generator. This is there in all engineering colleges, but in spite of that, when we ask students, even our own postgraduate students, a good number of them have not done any experiment, any serious experiment. I believe this is a very bad scenario, and therefore analog electronics and especially discrete circuits, simple discrete circuits, I would strongly encourage encouraging your own students to do this kind of experiments, so that they understand, they get a hands-on experience with hardware. Otherwise today we do not need to teach much into the analog electronics. Now in fact another trend which is there in the most of the western countries is that today you would find, if you go and buy a book, you would find that most of the books would have only a few pages on BJTs, and you would find the discussion has entirely changed from BJTs to MOSFETs. Now maybe in about 10 years from now you may not have any, let us say you may not get even BJTs, that is what people are predicting. But as you all would appreciate, it is extremely difficult to use a MOSFET and to do an experiment. So that way JFET can be easily bought, and again to teach concepts on FET based amplifiers we could use a JFET. Now you could give to your students one of the ways which I found which is very useful, this is in the context of multi-stage amplifiers, and as I said in almost every in any practical application you would see that you cannot build that particular application using a single stage amplifier, and you could give extremely simple applications to your students just for the sake of learning, so that they get enthused in analog electronics, that we should remove this fear of analog electronics. Now I can suggest maybe one or two simple, very simple things. For example, think about a kind of photometer, something which, don't worry about the accuracy of the photometer, but something which measures the light, something which can tell you whether, we know intuitively whether outside, whether it is dark, early morning we know just by the look of it we can say it's dark, if it is cloudy we know it's cloudy. Now you can have a simple photometer built around a photo detector which is very cheap, 5 rupees, very cheap, and a few discrete components. Now let us think about the simple circuit I talked about, a simple photometer, where don't worry about the calibration, but the interest is to see where at least it can show some relative changes in the voltages. Now as we talked about yesterday, a photo detector is essentially a current source. Now so far in all our discussion in the multi-stage amplifier we assumed it to be a voltage amplifier. Now here is a situation where we need a current amplifier. Now you may not be aware, but actually there are very simple circuits which can actually convert current to voltage. One such circuit is an inverting amplifier. An inverting amplifier can easily convert the light into a voltage. Let us talk about a current to voltage conversion. Now we know about we have studied the inverting amplifier using an op-amp. You could also use a common base amplifier. We said that in a common base amplifier the input resistance is very small, and we know from our discussion yesterday that if you have a current, then the input stage should have extremely low input resistance. Now you could think of a simple circuit like this, where we have a photo detector here, the light is falling on it, whatever photo current, and it is biased in a reverse mode by applying a positive voltage to the cathode there. Now here because of the negative feedback here, this particular potential is at virtual ground, which is 0. So here we have an ideal current, so this is a current to voltage converter. So we have this amplifier, the circuit we have here is nothing but a trans resistance amplifier. So we could think of such simple circuits which can be used for teaching analog electronics. So I would come to the end of my lecture here. Just to have a quick recap of what we discussed. We talked about multi-stage amplifiers, and we said the strategy in a multi-stage amplifier is to decide on how many stages, and we said in a typical multi-stage amplifier the first stage, assuming it is a voltage amplifier, need to have high voltage gain, need to have high input resistance, and the voltage gain need not be high. The second stage would have a high voltage gain, and the final stage would have a low output resistance. And we talked about examples like a public address system, we talked about the example of a op-amp. So in all these cases we see a multistage amplifier, and we said that in almost all practical application we cannot get the required amplifier specifications from a single stage. So we will go to Kanchipuram, where we will have an interaction. Yeah, over to you, Kanchipuram.
Thank you, Professor John. I am in Kanchipuram, and the audio video was very good. All the participants are very happy with your lectures, and there are around 45 participants. And I'll give the I'll give the mic to HOD. Maybe she can give feedback on the course.
Good morning, sir. This is Dr. Malari from SRM University. This is the first time of this virtual mode our faculty are being given exposure, and during the inaugural we feel that such an seminars of this kind or workshop this kind is necessary in the modern scenario, where we sit at our site and listen to people who have put good experience academically. One such thing is we have been talking and teaching for decades together the semiconductor devices and the fundamentals. When we listen to the inaugural thing, the first session of that, we could see that how to put forth to the students who have come from the +2 level, how to visualize it, and what we have perceived this idea or the concept, how to transfer to them in a very easy way of visualizing, so that, as you said, creating the interest towards learning the electronics is a fundamental thing that our teachers are given the exposure. And second thing is, during the laboratory sessions or the experimental sessions, it gives a way for the teachers to understand or answer the questions of why I am not able to get the output, because as you said, the students are not getting the output in the analog area. Why they have not got the results? For that, the teachers, they are getting an inside view of answering them. That is an highlight of this course, I could feel. And the second is the exposure towards the experimental wise, giving an exposure to the board, CPLT boards are all will be of use to for the first teachers to upgrade themselves. That's a thing from my side as a listener and first viewer of this program. Over.
Thank you, madam, for your feedback. I think it will be extremely important for all of us as teachers to enthuse our students in doing experiments, and especially we need to encourage our students that analog electronics is not something to be scared about, but by doing experiments, and they need to interpret the results and find out why, and that is what makes them better engineers. I think the topic like basic electronics, in fact when I teach electronics, I tell students that almost everything which we teach can be done in the lab. So that way the concepts can be easily learned and assimilated if they do side by side some experiments, and also try to understand, and they also definitely must make mistakes. Only through mistakes we learn, but they must know what mistake they made, and that is where a teacher would be of great help. In IITs, when our students do the experiments, the faculty also goes around, and when they say something is not working, we explain to them why, and therefore I think experiments definitely is the key. Otherwise it is just only theory, then they do not seem to get interested. So I think it is extremely important that we take a course like electronics, definitely a course like basic electronics or electronic circuits, digital electronics, all experiment and theory side by side. Over. We are going to Somia College now. Yeah, over to you, ma'am.
Hello, Professor John. I reached about 10 minutes ago, and I was sitting through the last part of your lecture, and the reception is very clear, audio video both very clear, and the font size is also, I think, quite legible from the back where I was sitting. Technically it all seems absolutely fine. I haven't had a chance to talk to the participants yet, but I will definitely come back with a feedback, I hope. Over to you.
Thanks Mukta ma'am for the feedback. I think it will be useful to get the feedback of the participants so that we could improve maybe in future or even the current sessions.